Hello everyone, I am Alava, an Ecuadorian student from Escola, and I would like to present our research work, Convolutional Neural Network from Wind Turbine Failure Classification based on SCADA data, developed by Brian Puruncajas, Ángel Encalada, Christian Tutivén, Yolanda Vidal, and me. This work was developed under the following outline. First, we have the introduction, which presents the background and important definitions, data overview and preprocess, where the flow of the data preprocessing is described, the CNN architecture, where the architecture and the hyperparameters of the neural network are defined. Section 5, where I present the result. The section 6, the conclusions. Let's see the section 1, introduction. In 2019, wind power met the 15% of the European Union electricity demand, was the primary source of new capacity in the US and Canada, the second largest in China. Failure detection systems are used to provide alarms about the deterioration of different components of a wind turbine, based on different types of information and sensors. The early detection and classification of faults in wind turbines have become essential to increase their competitiveness, since the prevention of faults and timely maintenance reduce the cost of repairs and the downtime of the affected turbine. A SCADA monitoring system uses data that is already collected in a wind turbine controller, and is a cost-effective way to monitor for earlier warnings of faults and performance problems. This work aims to detect and classify 6 types of wind turbine fault. Since the SCADA data shows the overall health of a wind turbine, it can be leveraged to detect when turbine performance is degraded and identify if a fault is developing. The Table 3 lists and labels all the types of faults that the SCADA system can record. We got labels from F1 to F6, and faults like pitch actuator, generator speed sensor, fault, 3 types of pitch sensor faults, and a torque actuator fault. In this work, a deep learning architecture known as convolutional neural network was implemented, which allows executing complex tasks like object detection or image segmentation. For a convolutional neural network to be able to predict, it needs to be fed by training data, so the model can learn in-depth features and patterns, which allows to obtain an accurate prediction. It should be noted that the training data is known from the model, in this case a recompilation of SCADA data of a wind turbine physical behavior. Let's see the section 2, the data overview. The data is generated from a wind turbine simulation model, with variable pitch control and variable speed upline. The main features of the simulated wind turbine are shown in Table 1. The elastic simulation software, FAST, is used to model the wind turbine. While traditionally, the sampling time in a SCADA system is 10 minutes, in this work it is proposed to reduce it to 1 second, using sensors with a frequency of 1 Hz. And to produce more realistic simulation of a wind turbine, wind modeling data generated from wind flow and stochastic turbulence software TurbSim is implemented. The inputs of the simulation are 10% of the intensity of a Cayman turbulence model, logarithmically wind velocity with an average of 18.2 meters per second, and a stiffness factor of 0.01 meters. 260 simulations of 10 minutes are performed. From these, 69 correspond to healthy simulation, and 160 to failure simulations, where each type of failure has 20 associated simulations, as shown in the Table 3. Each simulation lasts 10 minutes. However, not all this time is used, but only the last 400 seconds to avoid the transient behavior present at the beginning of the simulation. Section 3, the data preprocess. The data is stored in an array X of 90,744 by 9. Such number of time-step is given by the number of rows, the data. The number of volumes is equal to the number of sensor pairs, as shown in the Table 2, where we got sensors to measure the generator electrical power, the rotor and the generator speed, the generator torque, and the pitch angle for the first, the second, and the third blade, and the tower top acceleration. The data split process, the previously matrix X, is divided as follows: the 75% for training and the 25% for validation. This corresponds to 69,253 rows for training and 21,493 for validation. The data standardization process reduced the time for training, making the training more efficient. The data is scaled column-wise for the matrix X to be within a specific range from 0 to 1, based with the maximum and minimum values of the training data. The data reshape process, the main goal is to detect the failure in a reduced time of 3 seconds, using the available SCADA data. It is proposed to organize the available data on the simulation 3 time steps. This will lead to a detection time of approximately 3 sample times. Transformation is carried out individually for each of the 9 variables. Use a CNN input. As a result, we got matrix B with 3 times 9 columns. The section for the CNN architecture or the convolutional neural network architecture. The input matrix of the CNN has a dimension of 1 row, 3 columns, and 9 layers, followed by 3 convolutional layers and 4 fully connected layers. This data passes through the first convolution module. This module is made out by 14 filters, 2 by 2 kernel, with padding and stride equals to 1, resulting in an output size of 2 by 4 by 14, and the second convolution and the same kernel configuration, padding and stride as the first convolution, with an output size of 3 by 5 by 21. The third convolution has 26 filters, and the same configuration of kernel, padding, and stride of the first and the second convolutions, with an output size of 4 by 6 by 26. Finally, 4 fully connected layers, with size of 350 for the first, 175 for the second, 50 for the third, and 7 for the last one. Note that all these convolutional layers and connected layers have a radio trigger function. The final layer of the network is a softmax block used to squash the 7-dimensional output into a categorical probability distribution. 0 for the healthy, 1 for the hydraulic leak at the pitch actuator, 2 for the gain factor in the generator speed sensor, 3 for the stock value at the pitch sensor of 5 degrees, 4 for the stock value at the pitch sensor of 10 degrees, 5 for the gain factor at the pitch sensor, and 6 for the offset value on torque actuator. The section 5, the results. The figure 3 illustrates the confusion metrics for the validation dataset. The rows represent the true class, while the columns represent the predicted class. The obtaining overall accuracy performance is 88%. A precision of 100 is reached for fold F2 and fold F6, to a lesser extent for fold F4 with 85.5%, and the lowest precision corresponds to the healthy data. Regarding recall, the highest result is obtained in failure F2 with 100%, the lowest with failure F5 with 51.5%. For the F1 score metric, 100% is obtained for failure F2 and F6, and the lowest result corresponds to failure F5 with 65.5%. For specificity, the 100% is obtained for the F2 and the F6 failure, and to a lesser extent with the healthy data. Finally, the conclusions. This work, a promising strategy to detect and classify multiple wind turbine faults, is presented using only conventional SCADA data with an additional high-frequency sample of the sensor with 1 Hz. The proposed method does not require hand-design functions in advance, because the convolutional neural network learns the representative features automatically. A remarkable overall precision of 92.1% is obtained. This result shows that large CNN are promising to develop wind turbine fault diagnosis strategies. Future work will focus on two main areas. First, an investigation will be conducted to gain the ability to separate the unknown faults from the known and specific studied fault types. Finally, to face the validation of the proposed strategy in a more realistic environment, a downscale real wind turbine in a laboratory will be used. Now we reach the end of the lecture. I thank you for your time and attention. Here you can find our contact emails, and finally, I would like to know if any of you have questions about the presentation. Thank you.